Hello and welcome back. In the previous video, we have seen what are rotations and how rotations help in when you do AVL tree operations like insert and delete. And in this video, we are going to see the implementation of the rotation algorithm and how to use that rotation in insert and delete operations in this video. So just to get started, just to recall, when you do the insertion, once you search for the node where you want to insert the element, after you do that, then you go to the parent node and the height of the ancestor nodes might increase because of the node that has been inserted. So you keep going up and check whether the update the heights and check whether the AVL properties are violated or not. Similarly, in the case of deletion, so what you do is that first you delete the node and go to the parent, update the height, and check whether the AVL property is violated. So the one of the important utility function that you need is called the height, which will compute the height of the present node. So since we are going to update the height from the bottom of fashion, when I come to a node, we can safely assume that the height of the children of the node have been computed correctly. So once you make that assumption, then the height function is pretty straightforward. So if the node is not null, and then so if the node is null, then we are at the null pointer. We are by definition will return -1. If it's a valid node, then you check whether it has both left and right pointer. If it has both left and right pointer, by the definition is 1 plus the max height of the left child and the right child. If this condition is not true, then that means that it has at most one child, has zero number of children. If it has left child, then by definition it will be 1 plus um, height of the left child. If the right child is not null, then the height of the node is 1 plus the height of the right child. So if both the children are 0, that means that it's a leaf node, height of that is 0. So this is just the implementation of height. You are just following the definition of height. Height is equal to 1 plus the max height of both the children. We are considering the cases where some of the children could be null, right? That's all this algorithm does. The other function that I'm going to use is what is known as AVL. So this will return true or false. If the AVL property is violated, then it will return false. If the AVL property still continues to be true, then it will return true. So this just by the definition, you just look at the absolute value of the difference between the height of the left child and the height of the right child. If it is smaller than 2, then you return true, otherwise return false. Then we have to discuss the rotation function. So the rotation Z will be the node where the AVL property is violated. Then we defined Y as the child of Z such that height of Z is 1 plus the height of Y. And X was the child of Y such that H of Y is equal to the height of X plus 1. So after that, we defined these 4 cases depending on the relative position of X with respect to Z and X with respect to Y. So we'll just write the code for it. So you're given the node Z. Okay, so we are trying to rotate with respect to Z. So we want to define what is Y. I just go to the left child of Y, left side of Z, and check the height of this. If the height of this plus 1 is equal to height of the left child, then we can set Y is equal to Z left. If this condition is false, then the height of Z is decided by the height of the right child. So I will write Y is equal to Z right. And I have a variable to keep track which of the 4 cases it belongs to. So if I take a right turn, I will increment the counter by 1. If it's a left turn, I don't increment the counter by 1. So after I do this, I double the counter. Now again, I ask the question whether the height of y left plus 1 is equal to y height. If that is the case, then um, x is the left child. Otherwise, x will be the right child, and so increment the counter by 1. So height of x child and height of y, height of z, we don't know whether it has been updated or not. That's why we are calling this function. So here I could have written y left height, right? So y left height plus 1 is equal to y height. So I could have written x is equal to y plus left. So it doesn't matter. The edge function will actually compute the y left height. Okay. So just going back to the example here, in the case if I take a right term, so the counter will increment by 1, then it will be double, and then add 1. So this becomes 3, right? So at the end of this code, we not only know what our y and x are, and we also know which of the 4 cases it actually belongs to. So now let's look at the case 0, which is the left rotation. So the code for this is simple. So if you just look at these pointer changes, you have to make these pointer changes. And as I said earlier, this z is a subtree. So this subtree rooted at z will be replaced with subtree rooted at y. So if you are maintaining parent pointers, you should go to the parent pointer and change the child pointer to that. Right now, something is pointing to z. That should start pointing to y. That's the first thing that we're going to do. So you go to the parent and ask who is the left child. If the parent's left child is z, then the left child of the parent will become y now, right? So because after the rotation, this subtree is replaced with a subtree rooted at y. So the parent's left child, if it is z now, the parent's left child will point to y. If it is pointing to the right child, then the parent right child will point to y. So this is the first thing that we do in all the 4 cases. In 2 cases, y happens to be the root of the subtree. In 2 other cases, I will write here x instead of y. See, if this is not the case, if z parent is not is null pointer, that means that I am at the root of the uh, AVL tree. In that case, so this node I want to set the parent as y. The root of the subtree as y. Otherwise, after that, the pointers that you have written here is exactly the pointers that I have written in the previous slide. I just copied here. These are the pointer changes that are required here to make this rotation. After that, I have to update the height of the nodes y, x, and z. So the notice that after the rotation, x and z are children. So you have to compute the height of these two before you compute the height of y. So that's precisely what I'm doing here. So to do the rotation, compute the heights of the subtree, and that's it. That's the end of this case. Similarly, in this case 1, so exactly the same things will continue. So these pointer changes will be reflected in the code, right? So this point will remain same, and here what I have written here is what is just the pointer changes from the previous slide. So the moment you understand this diagram, this diagram, the rotations are reported as pointer changes, and that's what we report here. So if you are maintaining a binary search tree without the parent pointers, then wherever I am updating the parent pointers, those things you don't have to change. For example, if you look at these 3 are the parent pointer changes that I'm doing, and what I'm doing here is also updating the parent pointers. So if your binary search tree node does not have a parent pointer, then you don't have to update these things, right? So wherever there is an updation of parent pointer, you can just ignore it. Similarly, when you come to a zigzag rotation, the story is the same. So, but here the number of pointer changes are more. So you write down the pointer changes. This part is same. So all the pointer changes are reported here from here to here, right? So these pointers changes are just copied from the previous slide. And after that, I update the heights of x, y, z. So here x happens to be the root. So I should update the height of x after I update the height of z and y. So, and you also notice that the height of the root of the subtree is x. So this will get attached to the parent of z. Similarly, if you look at the other zigzag rotation, the same code. So I have to reflect the pointer changes that I have written here in the code, right? So that's precisely what's being done in this part of the code. So if you have understood so how this rotation happens, you can write down the pointer changes. Exactly the same pointer changes are written in the program. So in summary, when you want to do the rotation with respect to z, first you find x and y nodes. Then when you find x and y nodes itself, you can figure out whether you are going, which of the four cases that you're going to fall into. So once you know which of the four cases, then you have to just implement these pointer changes. So notice that each of the four cases is a constant time operation because it involves a few pointer changes and updating the height of your nodes. So each case is a constant time operation. So one rotation is, in our terminology, is constant time. In other words, order one. Once we know how to do rotation, so we will discuss how to do deletion. So what we said is that check if the AVL property is violated. If the AVL property is violated, just call the rotate function. And if this is not the case, then see if the height needs to be updated. If the AVL property is not violated and the height is also not changing, then your algorithm stops, right? So this is what you do after you delete a node. So, so notice that, so there were three cases when you did the deletion of a node. So we will not discuss case 2 because case 2, when you delete the node, it is actually a replacement of a node, and then you will recursively delete the node of predecessor. So we need to consider only the case 0 and case 1. In either case, what you're going to do is that you're going to cut a node and replace the child of that node with the parent. So when you do this operation, the height of the parent could change. So we start from that point. So after you did and deleted, so what I have here is the temp is the parent pointer of the node that you have deleted. Okay. So one of the child of this parent temp node has been cut. So now if the parent pointer is a null pointer, that means that you just cut a child of a root node. So in that case, you don't have to do anything. Otherwise, so what you do is that, so we are at the node temp now. Check if the AVL property is true. If the AVL property is violated, as we said earlier, so we just do the rotation. Once you do the rotation, in the case of deletion, so we have seen that there may be multiple rotations required. Then you go to the parent node. So, but I have written here parent of parent, because after you do the rotation, this will not be the root of the subtree. It will be a child of a node of a subtree. The no the subtree root will be either the node y or x. So if you want to actually go to the parent node, then you have to go to the parent to parent, right? So update the current pointer as parent to parent after you do the rotation. If this node now is a null pointer, then there is a flag. So the flag is false means that you are out of this while loop, right? So if you have reached the so when you went to the parent, if the root, if you have reached the root node, then you can terminate. If the AVL property is true, then you want to check whether the height is actually decreasing. So I send this the node and find the height of it. If it is smaller than the current height of this particular node, so what I set is that the height of this node has set as h, and then I check whether the parent pointer is null. If the parent pointer is not null, then I go to the parent pointer and keep checking these conditions, right? So in the parent point, since the height has changed, the AVL property might be violated in the parent pointer. So I have to go recursively to the parent and then check there. But if the parent pointer happens to be null, then I have reached the root node. So I can't go to the parent anymore. So I will stop. This else that I have written here is the case when the AVL property is not violated and height is also not changed. In that case, if you go to the parent also, the height will not change and the rotations will not be required. So in that case, you just set the flag as false so that the algorithm will stop the algorithm, right? There are three cases where the algorithm actually stops. So one is that after you do the rotation, you want to go to the parent pointer. If the parent pointer is null, then you can't go further. Or after you update the height, you try to go to the parent. When you try to go to the parent, there is no valid parent pointer. That means it's a root. In that case, you terminate. Or you terminate this while loop ends if the AVL property is true and height of the node that is presently right now is not decreasing. So if you want to write, so this is the code when the parent pointers are, if the BST structure has a parent pointer. So the BST structure doesn't have a parent pointer, then the code looks very simple because we do recursion. So when you want to delete a node, you start searching for the node. If you're going to the right, then what you do is that you recursively delete on the left subtree and make whatever this node returns, make that as the left child. This is what we had written earlier. So once this returns the subtree, what you do is that you compute the height of the node, update the height of the node, then check whether this node actually has violates the AVL property. If it violates the AVL property, just rotate, call the rotate function. So after that, return the node. Okay. Similarly, if the number is greater than the key node, then you want to insert in the right subtree and update the height. Check if the AVL property is violated. If the AVL property is violated, um, you rotate it, right? So after you delete, since the recursion in the backtracking, you keep going up. At each node, you will check whether the AVL property is violated, and if there is a violation of AVL property, you do the rotation. So we are not using the fact here that if the AVL property is not violated and height also doesn't change, then we wanted to stop. That's what the iterative algorithm does. But in this case, we don't know how to stop it. So it will go from the node where it is deleted all the way up to root, check whether the height is decreasing or the AVL property is violated. If the height is decreasing, it will decrease. If the AVL property is violated, it will just do the rotation restore and keep going up. So it's okay to go up all the way till the root node. So because the number of comparisons that you do is only log n. So in terms of complexity, this still continues to be order log n. But there'll be a lot of times where you'll be checking, updating the height of the node and checking whether the AVL property is violated at some nodes, right? So correct. Let's continue with insertion. So insertion, first you find the location where you want to insert that. After that, go to the parent. When you go to the parent, update the height of the parent. Then check whether the AVL property is violated. If one of these two conditions happen, then if the height changes, so you just call the height function and update the height. If the AVL property is violated, then you call the rotate function. So in this case, only there will be at most one rotation. So the moment you rotate, your algorithm stops, right? So, but if the height changes, but the AVL property is not violated, you may have to go up all the time, right? So if the height doesn't change, the algorithm stops. Okay, so this part of the code is after you finish inserting a node, right? So the temp is a node, it's the parent of the node where you have inserted an element, right? So Now again there is a flag. This flag will keep track when to terminate. So temp is the parent of the node where the insertion has actually happened, and compute the height of this node. Check whether it is greater than the height of the node that's already there. If that is the case, that means that the height of the subtree has increased. So once the height of the subtree has increased, then I ask the question whether the AVL property is also violated. If the AVL property is violated, then you do the rotation, right? So you do the rotation. So once you do the rotation, so after that, this while loop should terminate. So you set the flag as false. Else, that means that if the AVL property is not violated, then we want to go to the parent. But if the parent is not empty, we will go to the parent. But if the parent pointer is null, then we want to terminate. So so this is what happens if the height of the node is changing. If the height of the node doesn't change, then our while loop should stop. Right. So again, there are three conditions under which this while loop will stop. One is that height of the node that is presently there is not changing. In that case, we'll stop. In the other case is that you have reached the root node. So if you have reached the root node, then you can't go further up. Or if you do a rotation, the algorithm stops. So let's quickly look at the case we are doing insertion. The code for this also is looks very simple. So I want to insert, I want to find the node where to insert. If the key that I want to insert is smaller than the node key, then our insertion algorithm will insert in the left subtree and return the pointer and set that as the left child. If the key is greater, then you insert on the right hand side, right? So yeah, once you insert on the right subtree, whatever the pointer that you get, set it as the right child. So, and the original algorithm just return this node. So before I return this subtree, so what I want to ensure is that I want to update the height and also check whether the AVL property is violated. So I had to just quickly check whether the height is defined. So if the height is different, that can be done by calling the height function. Just set the height of the node as node height, and then check whether the AVL property is violated. The AVL property is not violated. If the AVL property is violated, just rotate it. Otherwise, we can continue. After you do this, just return the node. So once you have, if you are interested in implementing without the parent pointer, then both insertion and deletion, the code modification is very simple. So you have to just write the function for rotation, and so these are the three lines that you have to hand, so that so the AVL property is restored. So that's more or less what I had to discuss in this night, in this class. So, in this class, in a summary, we have seen how to implement the rotation and how to use this rotation in the case of insertion and deletion of a node in an AVL tree. In the next video, we are going to see how to, so what are some of the applications of AVL trees? What are the other problems that we can solve using AVL trees other than doing search, insert, and delete. So we'll take a quick break and come back after a while.